mathematical problem. To do the mathematical problem, we have to understand about the septic tank sections, the functional elements of septic tank. These two figures are from our book. This is in page 134 and this is in page 136, I guess. So you see, we can roughly divide the zones inside the septic tank like this: the slush zone, the clear space, sedimentation zone, and the scum zone. And in the slush zone, in the top layer, those are fresh slush, and bacteria is very active over there. So this top layer is called slush digestion zone, and the bottom layer is called already digested slush zone. So when we design these four areas, four zones separately for volume and for depth. Okay. And there is one more thing, we will discuss it even afterwards. That is, when we consider this design, this portion below this scum level, this length is very important, and also the clearance between the slush and the pipe edge is important, because if it is too close to slush will go out with water. If it is too high, then the scum will go out. So this placement is very critical. There should be a minimum distance from the slush, and there should be a minimum distance from the scum and the slush. So these things also should be considered when we consider the depth of the clear space. So when we do the mathematical problem, I prefer to do it in a table, and all the table have 4 rows. The top rows corresponds to scum zone, and the bottom row correspond to slush zone, and according to the place in the real septic tank, I place the rows where we should calculate. So let's see a problem from our book. And for each zone, there are some formulas are given in our book, and for depth calculation and for volume calculation. Let us see the problem from our book. So the book is this PDF file. So this is example 5 in page 150. Okay. So the problem states, design a septic tank to serve a household of 10 persons who produce 90 LPCD of wastewater. The tank is to be dislodged every 3 years. That means there are 3 data here. One is they have 10 persons. That means the population here is 10 persons. And then the next information is they have 90 LPCD, 90 liter per capita per day wastewater flow rate. That means the small q is 90 LPCD. And the third one is the tank is to be dislodged every 3 years. So the design life is 3 years. So if we look at carefully watch the formulas, you can see we need C and T is not given in this question. So first we have to find out what should be the C and what should we consider as T. So the rule about C is, if the sludge stays inside the chamber for longer time, they will be compacted, so we should take a smaller volume. But if the life of the dislodging cycle is less than 5 years, then we have to take a relatively larger volume. So in this case, n is 3 years, it is less than 5 years, so we have to take 0.06 meter cube per person per year. And T is the temperature, capital T is the temperature. For Bangladesh situations, we can take temperatures 25 degrees Celsius, because this is quite cold. If we design it for cold temperature, it will perform very well in the warm temperature. We will be risk free. So take it 25 degrees Celsius. Now what they have done, let's see what they have done with this problem. First they have calculated TH, that means this portion. So you can just see them side by side. You said 1.5 minus 0.3 into log P into Q, and that value should be greater than 0.2, and they have calculated 0.61. So this is from that book. And the next one is VH is calculated in this way. If we consult the book, this is from this book. Okay, 10 to the power minus 3 PQ into TH. TH means this value. So PQ into TH, so 0.55 meter cube. and next stage they have calculated this one, TD. So this is a mistake, this should be small t, okay. This is a typing mistake here. So in TD, just put the value of capital T, everything is given here. So 42.3 days, you can see the calculations here, and then VD, volume of digestion zone, this is 0.5 into 10 to the power minus 3 into P into TD. So just put the values, because we already got this TD, population is 10, so this is 0.21 meter cube, okay. And then they have calculated the sludge is CPN. So just CPN, put the values, we get 1.8 meter cube, and then they have calculated the total volume of this tank. You can see there is a dissimilarity between this formula I have written here and this formula in the book, but be assured this is the same formula, because V scum, so volume of scum is 40% of sludge, 0.4. So if we replace the V scum with 0.4 VSL, then this will become 1.4 VSL, okay. So but for my problem I have calculated it separately and added all of them. So I have calculated it separately and added all of them, but I put the book scan value here. Now what they have done, they have guessed the area of the septic tank as 3 square meter. So there is no answer why they have taken it 3. Should it be 5 for another problem? This is not answered here. So I will address this issue later. So what they have done to calculate the depths, let me show you. So first they have taken the area of the cross-sectional area is 3 square meter. So first they have calculated the sludge zone, depth of sludge zone. This means this zone, okay. Here is the calculation, 1.8, V sludge is 1.8, you can see is written over here, 1.8 meter cube. This should be divided by area to get the depth, okay. This is nothing new. So we are here. We have calculated just the depth of sludge zone. Now the next is scum zone, submerged scum, that means the top layer, scum zone. So scum zone is volume of scum divided by A, but instead of volume of scum they said 0.4 VSL, that means we already have calculated this thing. So we will put, instead of this value they have put this value, that means they are actually putting this value, right? Okay, they have calculated this scum zone depth, we also have calculated this. Now what they have done to calculate this part, why this formula is like that, let me explain this formula for you. To depth of the sedimentation zone is a bit tricky. We can calculate it by or like the other formulas, but we have to check for other things too. We have to calculate this part first and we compare it with 0.3, whichever is larger we should take that and add 0.75, and then compare it with this result, whichever is larger we should take the largest value. So first let me show you the calculation, then I need to explain it to you, okay. So first they have calculated this value 0.82 minus 0.26 A, and that value is 0.04, like this one, but this 0.04 is less than 0.03. So we are taking 0.3 wins, so we will take 0.03. Now and 0.03 plus 0.075 is 3.375. This value is 0.375. Let's calculate this thing and compare. So this thing is calculated 0.55, that means this value divided by area, and this is 0.183, which is less than the value here. So this value wins, and depth of this sedimentation zone is taken at 0.375, okay. So this value is smaller, so we take the larger value. Somehow in the book they forgot to calculate this part, so they have added this depth, and this depth. They forgot this part and calculated the total depth. Okay, total depth is 1.215 meter, and so they have decided the dimension of this septic tank should be 1 meter into 3 meter. That means area is 3 square meter, that means 1 into 3 meter. That also fulfills 1:3 ratio, and the depth is, instead of 1.2 meter, they have taken 1.5 meter because they are allowing some space for gas at the top. So before going to this explanation of A, let me explain why this formula is like that. To explain this, we have to go back to our figure here, this figure. You see, this 0.3 is the minimum depth requirement here, this B. This B, the distance from this outlet point from sludge should be at least 0.3 meter. So, and there is another formula to calculate this depth. This B is this formula. So, the minimum value is 0.3. We have to calculate it by this formula, but the minimum value is 0.3. So, if this result is larger than 0.3, then we will take that value. Otherwise, we have to take 0.3. So, this is this value, and then we have to also consider this value, the distance of this point from the bottom of this scum. This should be 3 inches, at least 3 inches. 3 inches means 0.075 meter. So, we have to add this and that to get this total depth. Okay, this and that to get the total depth. Then we calculate this value. If this value is larger than this the minimum requirements, then it's okay. Otherwise, we have to take this value. Okay, that's the explanation. But there is a big question here. What if the number of people is more than 10 persons? Should we take 3 square meter again? But what is the basis of taking 3 square meter as our calculation? To answer that question, I don't know what will happen. So, first let us check it by using our formula. That means let us design a small calculator to calculate these things. Okay. So, let us take the population is equal to 10. So, this is a bit different than this value, because we had added this extra value that has been forgotten in the book. So, so the value is about 0.07 larger than that value. So, up to this point maybe the calculations are okay, but if we take 30 people instead of 10 people, the volume will be changed. That will no longer be 3.28. So, should we still take a 3 square meter? That is the question. That this should not be 3 square meter, because if we take a 3 square meter, then the depth will be 3.15 meter, and 3.15 meter means very deep. That means this is about 10 feet deep pit, septic tank. That will look like a pit. That will not look like a box. Or if we have a bigger house, 60 people, look what happens if we take 3 square meter. Then what should be the optimum? Maybe we should take 15. Oh, that is not a good ratio. Maybe we should take 10. So, there is a problem in deciding what should be the optimum area. So, let me explain. To avoid this problem, I have that explanation. Okay, don't calculate this thing. First, estimate the area in a logical way. A septic tank should have a sweet ratio of length, width and depth. The ratio should, let us take the ratio A is to B is to C. So, the length is AX, BX, CX. That means, if the length is 10 feet, width is 5 feet, that means the ratio is 2:1. So A is 2, B means 1, and X means 5 in that case, something like that. So if this is the length, width and height, then the volume of the septic tank is length into width into height, and if we put the value X, then this is ABX cube, and so the X value should be this expression. That means for this septic tank, if we just decide what should be the length, width and height ratio A, B, C, we can calculate the X value, and when we get the X value, we can get the area value. Area means width into length, that means AB AX into BX, that means AB X square. Okay. So if we calculate like this one, then it makes more sense and things should be automatic. So let me get back to our problem, and we take this value. Let us put a value for A is equal to 3, as B is equal to 1 and C is equal to 1. So don't get confused, this C is the ratio C, not this C. Okay, don't get confused. So, and then if we already got ABC, value of ABC, so we can get the value of X. So what will be the X? So let's calculate X. X is equal to third root. That means we have to start with a bracket V. V means this value divided by A into B into C. A into B into C. Close the bracket and put the power. The power is 1 by 3. Third root means 1 by 3. So if we press enter, let us check the original formula, original math. So this will be 1.03. So the area, we have to change the formula of area. Area should be AB X square. So area equal to A into B into this value and square. So you see, for the previous math, this is very close to 3 square meter. If we take an integer value for this, for example, if we take an integer value for this one, then it becomes 3 and the result remains the same. But the advantage is, if we use 60%, that will not remain 3 square meter, this will be 10 square meter. So the depth will be more logical. If this is 100%, then this will not remain in 3 square meter. This will be 13 square meter, and the depth will be more logical. Okay. Maybe we don't need to put integer. Why don't we take the original value, whatever that is. So then we can easily calculate the length. Control right. Length is equal to A into X. So A into X, this meter. Width is equal to B into X, right? Equal to B into X, and C depth, that means D, is equal to not C into X, because we are calculating it in a different way. So meter and meter. We can just cut these values and put them here. Why? Because your client is not interested to look inside this, what is happening here. So these are the values we can always guess. So I am changing its color, maybe blue, and these are the values. I am putting them in blue because these are the values we are going to change. So these are the meters, and people will not be interested to see all these figures. So let's reduce the decimal points, and maybe we can write it in feet as well. If we prefer feet, equal to this value into 3.28. to 8 is the feet, and maybe we can consider this like this one, something like this. So in that way, that makes more sense. So whenever you change a value like the 10 in the problem, we get length is about 10 feet, width is about 3.5 feet, and the depth is about 4 feet. And if we consider or add some freeboard, this will be maybe 5 feet. But if there is a increase in number of the people, here automatically the area will be changed. This will not be 3 anymore, and these things will makes more sense. 17 feet long is about 6 feet wide, so 3:1 ratio is maintained and depth is maintained. Okay, so that is why I prefer this area should not be taken blindly as 3 meter. You always use a ratio and solve the problem. So that's all for this today. Thank you very much.